So we are being controlled by the random outcomes of a complex system. And in this talk, I would like to argue that these outcomes are not that random if we manage to understand them better. And that may lead us to wonder whether we are actually controlled, but I won't start any debate on free will right now, and we will just start delving into complex systems at first. Hello, welcome to my talk. It's actually the longest talk at the conference, just because I asked to talk for a longer time. And they accepted. So my name is Max. I work for the three organizations down there, and I will give this talk because some people ask me to give this talk. Some people ask me to talk about complexity because complexity seems to be overlooked, neglected in the movement. And if you want to categorize this talk is like a methods-driven talk, so it's rather meta. And hopefully it's the first talk of like this kind about this field, hopefully leading to more specific applications of complexity science and computational modeling to EA purposes. And if you want to categorize me, I'm first and foremost an aspiring effective altruist. And then I kind of started being interested in complexity science. So I didn't start with complexity science and computational modeling and then just applied patterns matching with EA just to give a talk at a beautiful conference like this one. So I thought that like these methods are actually helpful for actual EA purposes. So before actually delving into details, I have a set of prompts. And the first one is that if we actually look outside in the world, we can look at different systems, and we can kind of agree that like these systems on Earth are quite dynamic. So we can look at like social systems of people interacting, exchanging goods, of wealth being distributed in a certain way, and this keeps changing, and this is dynamic. We can look into nature, which is not that different, where you have the number of species that is changing, you have the environment that is interacting with the social environment, etc. So like, things are quite complex, things are dynamic, we can observe this with our own eyes, it's not that difficult to agree on this. But what's interesting is that if you actually look, if we actually look into more details in this system, we see that there are dynamics, but that they also exhibit some resemblance. So this is an example from a study by scholars in Utrecht University. That was quite a chance to find this. That actually looks at distributions in a social system and in a natural system. And they actually find like profound resemblance between both. So they looked into wealth distribution in the world and found out that like around 1% of people own 50% of the resources. And they looked into the Amazon forest and found out that like 1% of the species actually has 50% of the biomass. And they were like, oh, okay, but we can't find 1%, 50% a bit everywhere. So let's look actually deeper into this. And they found that like the math that explained the way these distributions actually happen are the same in both systems. So even though the mechanisms that produce these distributions are completely different in both systems, they managed to find common properties in both systems, systems that are dynamic, systems that are profoundly different. And that is kind of like a first prompt that justifies the existence of one field to understand complex systems that are different, but common properties to explain them. My second prompt, and this is why I have a Rubik's Cube in my hand, I just want to take like a problem-solving perspective at like looking at systems and trying to understand reality. Is that like if someone wants to understand something, or if someone wants to solve something, the person can use different methods. And the person can be quite stupid to the question and like just keep doing the same thing over and over. And this is literally like an illustration of stupidity because we will never manage to solve the Rubik's Cube if we keep doing the same thing over and over, okay? The person might use another method that is so much better, that is just like trying to do random stuff continuously without any learning. And this is so much better because at some point it will take ages, but the Rubik's Cube will be solved. And the third method would be to be a bit more systematic about the Rubik's Cube or about any problem in general, and to actually understand the gears of the problem, the gears of the system. And by doing so, we can actually test some things, learn from it, and just try to be systematic about the problem. And if we actually think about reality that way, we can have a set of methods that we like to apply, but since systems are quite different from each other, since reality is quite complex, we might want to think that like the best method is at least not to have a fixed one, that we can change the methods that we use. And that hints back at how to understand dynamic systems. The third prompt is this common distinction between the map and the territory. So the map being our understanding of the reality being the territory. And all maps are wrong, and that's okay. And that's actually why they are maps. So maps are meant to be useful. They're meant to show what we know, what we don't know. They're meant to be used. This is why they're wrong, because if our maps are reality, then we just can't manage to compute everything. So our main goal as EA is to create good maps, right? But the problem is that sometimes people tend to over-marry the map and the territory. And that's like a form of intellectual hierarchy which just prevents everyone to understand everything. So what we want to do is to always focus on map, let the territory alone, and enhance the type of map we have, enhance their quality. So summary of prompts. First of all, system are adaptive, dynamic, but nevertheless may exhibit some resemblance. How can we understand this? Second, to solve problems, we can use stupid, random, or systematic methods, and fixed methods are likely to be the worst. And finally, we all create maps of territories, and sometimes we confuse them, and the ultimate goal is to avoid the confusion and improve our maps. So those are the prompts for my talk, and my talk will cover the following. So first of all, I will go through the field of complexity science, so that's mainly theoretical. Then we will switch to computational modeling to explain why we model, what it is, and why it might be useful. And then at the end, I will give some examples of applications of computational modeling and complexity science that are directly related to EA topics. And at the very end, I will give an example of a project that we are starting in Geneva that relies on this body of theory and methods. So complexity science, first of all. Complexity science is a scientific field that was created by a bunch of scientists. Most of them were from the Los Alamos National Laboratory, who gathered together in Santa Fe and wondered, how can we have a scientific approach that actually does the synthesis of other disciplines while not being reductionist, while not being a discipline itself, and while actually fighting against the specialization that is prevailing in science. And their idea was just to synthesize disciplines at first, and they actually went beyond this and developed a set of methods, a set of like properties and tools to analyze complexity. But okay, what is complexity? Everything is complex, and our life is complex, EA is complex, EA ideas are complex. What can we do about it? John Holland, who's pretty famous in the complexity science sphere, just says, so complexity still remains loosely defined, and that's okay. However, it does not prevent one to have a systematic approach to the subject matter. That's fine, oh, okay. It makes me comfortable. The second thing is slightly more advanced. So like complexity characterizes something with many moving parts, where those parts interact with each other in multiple ways, displaying nonlinear patterns in the aggregate, which often is not additive. This something usually is called a complex system. So this is already like a better definition, but that is still quite meta and a bit blurry. But at least it gives us some indication. And to actually understand system, I would like to take the analogy of a chess game, a chess board, to go through some of the basics that we apply in system theory. So the first one is the concept of state. So the state of a system is how the system looks like at time t. It's like how the chessboard looks like at a certain point in time. And then the states basically evolve. And the states evolve according to a set of rules that will determine how basically the dynamics function in a system then will create other states continuously. So for example, this is the current state of a chessboard, and on this board we have 8 times 8 squares, and we have 32 pieces of 6 different kinds that just like move. And those are the rules that create states. And one particular property of complex systems is that there is perpetual novelty in the system. So we can know this, a starting state, we can know all the rules, but there will always be new patterns, new ways, and it's almost impossible to predict an entire chess game based on the state that we actually look at as a certain point in time. So there's kind of this stochastic process that happens in a complex system. But the good thing is that it's not entirely chaotic. We can still understand that, and we understand this by actually looking at patterns. And that's the key thing in complexity science. We try to look at patterns and how they emerge from the rules that will change the states. And so the thing is that if there are no patterns, then it's completely chaotic. That means that we can't understand anything. If we can predict any pattern, that means that the system is simple, okay? And if the patterns keep changing, but we find some resemblance and some recurrences in the patterns, then the system is complex. And actually, most of the systems are complex. Very few are simple, very few are chaotic. So complexity science, in order to understand these patterns, mainly look into the micro-level dynamics of a system. Rather than looking directly at all the states, we try to like deep dive into the micro-level dynamics. And that should change. Yeah, nice. So here's an analogy. So we have Lee, and Lee is quite happy because it's sunny today. And Lee has an ID because there is Sam over there. And Lee wants to give a gift to Sam to seduce Sam. But Lee sees that Sam is not very happy, so F. And Lee learns from that and actually adapts and updates, and Sam then becomes actually happy. Okay, all great. But then there's actually Kim that sees this and that is unhappy, which makes some updates because S, and will make Lee also update, acknowledge that it was a bad idea, update and adapt their behavior. So the question here is like, you have different agents that have different attributes and different rules of behavior and preferences. But you also have like an environment that may changing. So would the situation be different if it was completely rainy and if Lee had an umbrella? Maybe not at all. Maybe Lee would have found a strategy to do something better. We don't know. But that's basically what complexity science specifically looks at. And like how different agents that have a topology of interactions, different agents that are all different, they are heterogeneous, that have rules of behavior in terms of what they do, how they adapt, how they learn, and how they update. They have a topology of interaction, so that means that some agents may be connected to others, but not to the others on the other side. And they are like feedback loops that are the things through which information travels. And then these agents, they behave in an environment that is also changing, that includes stressors and shocks. So for example, a stressor might be like a population that lives in a democracy that has certain rules. This is a stressor. And then you may have some shocks like elections or votations, and that will just change behavior or people or perceptions of people. Okay. So this is a quite simple example. But now what if we look at like thousands of agents constrained in an environment that is co-producing the patterns with agent behavior and the environment changing itself. So it becomes a bit complicated, and that's why we will turn to computational modeling at some point, because we need to formalize that to understand. Only with theory, it wouldn't be possible. So just like as a summary, on the micro level, what we look at is the adaptive behavior that just keeps changing over time when you have other agents that behave in a certain way. When you have the environment that changes, then the agents actually adapt. And we do this to look at then macro level dynamics. So that are basically the outcomes of what happens on the micro level. And they have different properties. So one of them is what we call self-organization in patterns. So this is a map of New York, and we see that there is some segregation based on people's preference, or it might be top-down, or we don't know. But in case it's based on people's preference, this is self-organization. And there is a quite famous model to explain this, which is called the Schelling model, which basically explains that how two different agents that have only one parameter, which is their willingness to live close to someone else, then just produce in the aggregate patterns of segregation. And in both cases, agents actually prefer to live with people that are different. So agents' preference of 30%, that means that 30% of the time, they would like to live closer to people that are similar. So that means that 70% of the time, they prefer to be with people that are different. And same with 45%. But the problem here is that we could assume that there wouldn't be any segregation with only 30% of micro-level segregation. But in fact, in the aggregate, we find that there is. And that therefore, the aggregate is not the sum of all the parts. It's just something different, greater or not greater. Another example of self-organization is this flocks of birds that we can observe. So each bird is kind of independent from each other. They fly where they want, but there is this coordination that happens without any central control, giving birth to these beautiful shapes. So this is something that complexity science also tries to understand, not only on birds. Something else that happens in complex systems on the macro level are these nonlinear effects. So you have agents interacting on the micro level, and what you find is that at some point, then everything changes. Or you have a huge event happening from nowhere. But why is the case? And why is the case is basically the whole question of complexity science. Sometimes it's just about power laws and nonlinear effects. So this is completely different from what we sometimes intuitively assume in terms of linear relationship between two variables. In complex systems, you just don't assume this kind of thing. You just look at what happens, and you try to understand what happened before the nonlinear effect happened. And that's where the butterfly effect analogy comes into place. There is an example of a model that shows this, which is a forest fire model, where you have one parameter only, which is the density of the tree. And you have a fire coming from the left-hand side, and then you have the percentage of the forest that is burned. And in the model on the left, the density is only 58%. And on the model on the right, the density is 59%. And we could just assume that it's the same, because it looks exactly the same on this grid, 58 and 59%. But with this extremely simple model, we can explain nonlinearity, because with just 1 more percent of density, we reach a percentage of forest burned of 70%. And this is completely nonlinear. What we observe if we vary other percentages is before 58, it stays the same. You have some outliers, but most of the forest burns to 10%. But once you just switch to 59, everything changes. So this is of the interests of complexity science. And one underlying other dynamic is the concept of power laws, which may be about like the probability of events happening, and that like huge events have a lower probability to happen, but they nevertheless happen. And it can be also about the distribution in networks, that like some nodes have way more edges than others. And this is, again, very, very different from what is applied in mainstream research, normal distributions. And this leads us to extreme events, which is basically one of the study of complex systems, is like the study of black swans. That like those huge events that we cannot anticipate because they have such a low probability and that are hard to study. But there's actually this other concept of Dragon King that is theorized by Didier Sonnet at the ETH in Zurich that basically says power laws distributions are not the only thing that happens in complex systems. You may have way weirder distributions that may actually arise. And that's mainly because he theorizes huge events as small events becoming big over iterations. And he basically says that like we may have extreme events that may happen with actually a fairly high probability. And he does this kind of analysis with financial crisis and crashes in the economy. So two other fundamental properties of complex system is this idea of non-equilibrium dynamics. So sometimes when we think about the system and we want to model something, we ask ourselves, so what is the equilibrium here? What is the system trying to optimize for? And in the case of complex science, we don't try to do this at all. We just try to actually figure this out. How things actually evolve that way do not converge to equilibrium, but just like displace some terms over time. But the notion of equilibrium does exist in complexity science. And sometimes we may just observe like multi-equilibria dynamics. So that's, for example, like a system that alternates between two states. And overall, that is just like a set of properties and methods that are completely different from what we tend to think ourselves, but also from what we find in mainstream science. So linking micro and micro level dynamics, that's kind of like the thing we want to do in complexity science. And one idea fundamental to this is that the macroscopic properties that emerge from micro-level dynamics, it's basically the system macro property is different from the sum of its parts. So there's this concept of emergence that some people talk about. Emergence is a bit blurry as a term. It would be more right to say like there's something that emerged from something else, okay? And then like, this thing that emerges from something else is not just the addition of everything that we observe on the micro level. It's like different. So there's this common sentence of the whole is greater than the sum of its parts. It's almost the same, it's just like different because it can be smaller than the sum of the parts or bigger, etc. And then there's this other thing that the relationship between micro and macro often is stochastic, meaning that like the starting state of a system gives you almost no predictive power on the mature state of the system. And this is why complexity science tries to explain things rather than predict. Because the argument there is that like almost any error in the measurement on the micro level will just lead to huge errors in the macro level. And one example of this is this model of 10 ants that have the same behavioral rule, that start with the same starting states, the same speed, and the three models last the same duration, and it's exactly the same, literally exactly the same on the micro level. But what we observe in the aggregate are three completely different scenarios. And those are 10 ants that are exactly the same with the same behavioral rule, 10 single ants. So, and we observe such a complexity when we just run the same model twice. And this is just like an example of how complex systems may just produce stochastic outcomes. And this is basically the study of and raison d'être of complexity science. And we can argue that, like, economics, for example, they do look into complex systems, and they argue that they try to understand how complex the economy is, and that's true. And systems have been analyzed already throughout history, but not necessarily done via such insights. So as examples of complex systems, just to grasp the concept a bit more, there's this concept of ant colony of, like, small agents that are very, very simple in comparison to the whole that create, like, this huge complexity. It can be stock markets. We have agents and group agents that behave in a certain way, that interact, that lead to non-equilibrium dynamics and some outlier events. Policy might be a good example. We have agents and group agents interacting, leading to big decisions having small effects and small decisions having huge effects. And then finally, the field of artificial life is actually the field where complexity science has been mostly applied, and is mainly about, like, how things might evolve and develop intelligence through learning and evolution. So it might be quite easy to agree with all of this complexity jazz, because it seems quite obvious. Or at least it might be easy to be interested in this complexity jazz. But what's not obvious is how can we actually integrate all of this in traditional research? And if we look at traditional research, we actually find practices and ways to consider things that we don't find in complexity science. So for example, in traditional research, what we've mainly done so far was applying reductionism. So we try to understand the parts of a system rather than the system as a whole. The parameters in a system seen in a reductionist way are specified in a precise way. They do not necessarily fluctuate. In traditional research, we also tend to assume, like, the presence of an equilibrium, that things are maybe static, that, like, the system is optimizing for an equilibrium. We tend to assume that, like, the agents in the system are rational and that the agents themselves are homogeneous. In complexity science research, we rather look at the whole system, or almost the whole system. We try to look at, like, how things are, like, flexible and versatile in terms of parameters and agents. We try to look at, like, the dynamics, so rather than how things move, rather than how things stop. We try to look at, like, the processes that may lead to patterns. We try to look at, like, networks, how things are interconnected. And there's this fundamental question of, like, adaptation that we specifically look at. We also suppose that agents are bounded rational. They have cognitive limitations, and they're not necessarily super intelligent. And we also suppose and want to specify heterogeneous agents in the analysis, because that's from where the macro properties will come from. So this was my first section on complexity science. It's pretty theoretical and pretty meta. Now we will switch to computational modeling to see how the theory itself can be actually operationalized to explain concrete phenomena. So one question is, why model? And quite often in Geneva, when I say that, like, I try to model policy making, I try to model risks, or I am interested in resilience, people are directly quite interested, and they relate to the topics because they seem to be obviously quite interesting. But when I emphasize the fact that I want to model things, people say, but why model? And they become super cold. And what I reply is, like, but you have models in your minds, so that's why I model. I just try to have more explicit models. And new models that you have in your mind is just an implicit one that you cannot test and that we can't verify. So we need to be explicit. And more concretely, we need to model for different purposes. So in some cases, we model to actually predict something. This is not really the fact in complexity science, but in some instances, it's meant to do so. We model to explain, which is completely different than predict, to explain some processes, to just explicitly say what the micro level of a system is. We model to guide data collection. Sometimes on complex topics, we don't really know what we need to collect data about. Therefore, we model before in order to collect data after. We can model to eliminate core dynamics. So for example, if I would have asked you to have a mental model of a forest fire of 58% density, of a forest of 58% density, and the same behavior of 59%, I'm not sure you would be able to like actually imagine the core dynamics of such system. Then we can also suggest dynamical analogies. So for example, between the natural system and the social system, as we've seen, we can discover new questions by challenging the model. We can promote the scientific habit of mind, because if we only model in our mind, then we can do everything we want. Well, if we actually put things on paper or in computers, then it becomes a bit more systematic. We can also bound outcomes into like plausible ranges. So some analysis in complex systems are just about like, okay, so what are the main patterns? And then what are the outliers? And then basically it's just about arguing that like, okay, those are the main patterns, those are the outliers, and we don't talk specifically about some patterns, it's just about the set of them. We model to eliminate some core uncertainties, to sometimes offer like crisis options in near real time. So if we have a simulation, a model at hand about a specific topic that is of high importance, then we may actually run simulations when the thing happens in order to see what we can do. Then we can try to explain some trade-offs and like suggest some efficiencies in the system itself. So if we see that like we have a system that is dynamic, but it's not efficient at all, we can try to change parameters to see how it may change. We may want to challenge some like theory by doing modeling and then test the model. So sometimes on very complex things that we can't really collect data for, all we have is theory, and we can build computation models to then actually change the parameters, change some parts in the theory to know like how in the aggregate things will change. We can suggest, refine, and interpret experiments. So I will talk about this a bit later. But for example, let's say we want to have interventions in developing countries, and we don't really know what to test, how to conduct the RCT. We can do some modeling beforehand and see some dynamics that may then support which RCT to conduct. We can use model for like other purposes, like trained practitioners, to discipline the policy dialogue around like a certain model rather than around people's mind models. And we can educate the general public if we have good models and that are understandable at hand. So what's the modeling process? How to actually create one? So what we mainly want to do is to translate what we have in the system into like a computation model. And if we look at segregation, we can look at like reality more like this and collect some data, and based on this state some variables, and this will be basically the input of the model. Then we can look at some the rules of the states, that, for example, the interactions, the rules of behavior of agents, and specify this in the engine. And the engine will then produce an output that we then try to compare, if possible, with what we observe in reality at time +1, 2, or 3. So the modeling steps are basically the following. What we try to do is to have like a conceptual model of the system that we describe qualitatively first, usually via a diagram, and then we try to translate the relationships into math. And we can use differential equations to explain the relationship between two variables or two parameters. We can use phase transitions to explain how like a specific agent may vary its own state, or how like the whole system may actually change, or we may actually rely on critical phenomena math to explain the creation of power laws or like nonlinear dynamics. Then once we've done this, we need to convert the world into code, choosing the right algorithms that capture the conceptual model and the math, and choosing the right programming language. Most of the models are in C++, Python, some in like JavaScript and MATLAB also exist. And then at the end, what we need to do is to do extensive testing. So we need to check whether the code, the math, and the model reflect what we have or what we could get from reality. And then we need to test some simple cases to run the model and to actually construct the model on something really specific. Then moving on like different bigger cases, a bit more complex, adding some more complexity to see whether the model can actually handle that. And at the end, we can validate the wall and compare to like external data sets. So the other question that I receive in Geneva after the why model question is, but why using computers? And my usual question is, but you have a computers in your mind. And you do compute every day, and you have very limited computation power, and that's why we rely on computers, just because they have more computational power. So the problem that we have in, so it's inverted, interesting, that we have with our limited computational power is that we can have a really good detailed micro-level model in our heads, but in order to imagine what will happen on the micro level, we will need to take a lot of mental shortcuts. And those mental shortcuts might be really good, but might also be really bad, but it's unclear and not explicit. So what we just want to do is to rely on more inputs that we just put in a computer to have more computational power, to process more parameters, more variables, and to have an output that comes directly from the input, and to be able to run the same input many, many times to see whether different dynamics may be possible. Because if you do this in your mind, it's not necessarily clear that you think about the same thing twice and you will come to the same conclusion twice, because you may change your beliefs, change your perceptions in between. So in most of the scientific period so far, what we've done are theory and experiments, and the back and forth between the two. So with like deductive and inductive reasoning and logic. And what we can do with computational model is just add computer simulations to our set of tools. And we can do deduction and induction with computer simulations, but what we can also do is generating data. And the data that you can generate with the computational model, then you can use them to do deduction and induction. So that's how it complements pretty well how science has been done for long years. So what are these models that actually generate data? One very common type of model is this agent-based type of model that may actually reflect the most closely the theory that we find in complexity science. So that's basically when you have an environment that is changing and you have agents in this environment that are heterogeneous, that are interacting, and you run the environment and the agents and you observe what comes out of it. This is agent-based modeling. You can have network-based modeling to see like how things are interlinked. Can be very useful to model like global pandemic, for example. This so far has been mainly used to do some World Wide Web analysis. You can use computational game theoretic models that basically is like a advanced version of the game theoretic models that we know, like Prisoner's Dilemma, Stag Hunt, or Chicken, but just over iterations with like learning processes. So typically you have like a population N to start of like different agents that have different strategies. They go into game rules, so they basically participate in tournaments, and then switch to like replicator rules. So there will be a selection effects based on agents' fitness, and agents will also be able to change their strategies based on the strategies used in the tournaments, and then that will lead to a population 1. And then we can iterate this and see how agents adapt the behavior in game theory. We can also rely on system dynamics. So this is a system dynamic model of the effect of like a new product that comes into the economy. And we use this to like specify variables that are not moving but only changing and only interacting with each other. So this is one model of like a new product. This is one model of circular migration in Southern Europe. So of like people moving in different stages and the stages interacting between them. And in the loops, you have basically people moving. So models can be used for two main purposes. So the first one is to do like exploratory or like theoretical modeling. So that means that we have a complex system or a problem that is extremely complex, and we don't have a lot of data about that, and all we have is theory, and we just model to do more theory, or like to test theories or improve theory. This is something where we can do by like generating data that can just illustrate what we mean by the theory. But we can also do something else that is more evaluative and data-driven. So for this, basically, you rely on data to start the model, and then you compare the model results with the data. So this is some details on how the data can be used in model. Data can be used to seed the model, so you can have data on the micro level, on the agents, their beliefs, their decisions, etc. You can use data to calibrate the model. So once you run the model, you want the model to go into the right direction. So you might use data to just introduce some path dependency. So just so that like the model represents reality better. And at the end, you use the same data and other data to validate the results. And if you actually do the 3 steps, that's what we call evidence-driven modeling. So that means like computation modeling, sometimes like it's quite difficult to argue that like this is a form of evidence because it can be like purely theoretical and you just generate data from something you specify on the micro level. But if you actually rely on data and you see it, calibrate and validate with them, then that actually may produce outputs that can be qualified as scientific evidence. So some applications. So this is the graph of the results of a computational game theoretic model of different agents that actually adapt their strategies in games. This is an agent-based model that try to model different behaviors in interacting in stock markets. That may lead just to like non-equilibrium dynamics and things constantly changing. This is a system dynamic model of policy stages. So policy making can be understood as like a set of stages between like agenda setting, policy design, policy formulation, then policy implementation and evaluation. And this model looks at like the interaction between stages. And then this one is a network-based model that looks at like social media big data and to try to predict infectious disease spreading based on like the network structure in social media and based on the data collected from the social media. So that might be quite exciting, and actually, like, there's an increasing number of people that want to do modeling and that do modeling and that advocate for more modeling on anything. But in fact, there are quite a lot of like pitfalls and limitations because a lot of people model and they do crappy models. And there are some things we need to be careful about. So the first thing is that all models are wrong. And this is why we model, right? So we model to build better models because all models are wrong. We need to keep in mind that like all of these models are just representation of reality that we try to improve, but they're not fully accurate. Then other thing is that like models cannot prove a mechanism, but can only disprove mechanism or suggest that like one mechanism is enough to produce such output. Because once you actually put something in a computer, you can generate like any curve with any kind of mechanism, but that doesn't mean that those mechanisms are right. But you can say that, okay, this mechanism is actually enough to produce such outputs, or you can actually say these mechanisms actually are not enough to produce the output of interest. Then models cannot replace experiments. They can only complement them, as I already said. And also that the replication of model results are clearly needed. So again, you can generate a lot of data with models. You can claim that you try to understand complexity, and then you have really beautiful like nonlinear dynamics, etc. But again, I mean, you can generate this quite rapidly doing like 20 minutes of Python code. So we want to replicate this, and that's another dilemma that we have in science, is that we just don't have time to do it, but it's clearly needed. Models have clear problem in external validity. So even though you can adapt models with the same variables to different contexts, it will always be difficult to say the results of this model will be applied to like other situations, other circumstances, etc. Only based on the model results, right? Then one important thing is that models are not computer games. So that's kind of the third question I receive in Geneva when they say, oh, you do simulations of policymaking, but that's like a computer game. And they say this probably because I said computer, agent, environment in the same sentence, and because I seem quite happy about it. But in fact, it's not a computer game at all, and the goal is not to have computer games. Because computer games are way too difficult to analyze and understand. It's way too detailed. So what we want to have is like way more accurate maps, but are not that complex, okay? And again, what we want to have is maps, and that's why model remain maps. That's why model remain wrong, and that's completely fine. So that was my second section on computational modeling, and now I will turn to how all of this might be useful for EA purposes. So there's one thing that might be of interest, is basically risks modeling. So when we talk about huge risks in EA, sometimes all we have is philosophy. We don't have many data because those are so huge risks that we can't have data for. And we have some crucial considerations, or people just like working on developing technologies, right, etc. But it's very difficult to have like a quantitative approach to these huge risks because they just don't happen, right? But what you can do in risks modeling is to actually just simulate how the risks might spread. And this might actually enhance our understanding of the subject. So this is a network-based model of how global pandemic spread around the globe. So that means that if you model this, and if you get policymakers to look at such model, they might actually understand that like to face a pandemic, you may need to be prepared well in advance. And then that too late is actually too late. Then this is the results of an agent-based model of bioattacks, of, for example, terrorist attacks spreading infectious disease around the world. And this is the result of like an exploratory model of this kind. And this is extremely powerful because sometimes like facing risks is very difficult because you have an impact if the risk doesn't happen, so it's a bit strange. It's risks that like are likely not to happen, so you just can't collect a lot of data about them. So what you can actually do is to generate data and then feed this into the theory or feed this into the policy practices. Another application is to complement these experiments. And it's funny because I had to remove the graph I had in the before, but I'm just not allowed to show this. Otherwise, the UK government may not be happy. But so in Geneva, I'm involved in a project that tries to use an agent-based model to simulate household behavior in sub-Saharan Africa, and the household behavior according to food production and food consumption. And we try to see like how this behavior changes when you have shocks in the environment, when you have a drought, when you have a flood, when you have a conflict, etc., in order to see some malnutrition patterns and to see like the resilience to malnutrition of households. And once you have this running, the goal is to test some aid interventions in the model. And that can be extremely helpful because when it comes to not just solving one disease, but actually solving something that is way more complex and structural, like food security, and that directly relates to behavior, then you may want to have some more granular analysis than just RCTs. And this is, ooh, yeah, I'm not allowed to show this. Yeah. So this is how models can be used to combine RCT. So when you want to conduct an RCT, you have a population that you need to divide in two with a control group and the treatment group. And at the end, you will have some results, and from this, you can infer some causal effect. And I mean, we kind of know this in EA. That's kind of one of the best methods we have at the moment to determine the influence, the effectiveness of a treatment. But there is some debate that you can actually read on the EA forum at the moment, is that like the results of randomized controlled trials have a very, very low external validity. So that means that like the results of an RCT are quite difficult to replicate in another system. So what you want to do with, for example, agent-based models is that you rely on the same population that you will analyze, but you just run the same simulation twice. So you have like the whole population going through the treatment one time and going through the control one time, and you observe the results. So which might give you some more granularity, plus you may test some other parameters in the model. So you can test some other counterfactual scenarios. So let's say we have this treatment that we test in RCT. Let's test exactly the same situation in the model, but let's also test the same situation with a shock in between to see whether something strange would happen. And
Max, you have 1 minute left.
Okay, cool.
Maybe you have one final point you want to make, and then
yeah. So I will talk about this because this is redundant with the rest. So my concluding remarks are just the same than what I said. So we'll just talk about this. So in Geneva, we are at the moment consolidating the plan for using complexity science and computational modeling for EA purposes. And this plan is actually about trying to do modeling of existential risks that actually are possible to model. So for example, like a global pandemic that may spread. This is one side. The other side is doing modeling of policymaking, so modeling of teams in institutions that may interact about the specific risks. And there we can specify the agent's beliefs, the agent's possible decisions, etc. And if we combine both of them, if you actually merge them, you can test some, you can like generate some results and some insights on like how policymaking might change if you have something about the risks that changes on its side. And based on this, you can make some recommendations for the X-risks community, for example, for organizations to use like their research insights in a better way once they communicate with policymakers. We will give like papers and talks, but more importantly, what we can do is to conduct educative workshops for policy communities, and for this we can rely on serious games, or what we call scenario exploration systems. So those are basically board games that policymakers can play, and they interact on the scenario of a risk. They can make decisions, they can interact, and then you can reverse engineer and tell them, oh, maybe it went in the wrong direction. Let's actually look at some evidence, some research. Let's do some applied rationality training, and then iterate the game. And this can last 3 hours, can be like highly and heavily like experienced for policymakers, and potentially over time improve policymaking with respect to a risk. So this is how we would use this field specifically in Geneva for policy and X-risk sphere, and that also can also create like a network of people that can interact more closely on the matter. So for example, policymaker at the World Health Organization trying to work on global pandemic, interacting with people of X-risk organizations that can provide expertise on how a risk might actually happen. So I think I will just say thank you.
Thank you so much.